Right, let's talk about the size of this set of computable numbers, because this tends to confuse people, especially mathematicians. Do you remember we talked about Cantor's diagonalization arguments? And the mathematicians have this strange concept that the real numbers are bigger than the natural numbers, because you can take your candidate list of real numbers and always go and find another one that was missing from the list. So just in case you ever get into a fight with a mathematician, this is to explain how that pans out for the computable numbers differently from how the mathematicians do it. So you may be wondering that there appears to be a paradox around these numbers now. We have seen that computable numbers are a subset of programs. Yeah? We've said a computable number is a program which takes integer k and outputs an interval, but it's only classed as a computable number if it also has these properties of convergence, about the cat wiggling his way to a point. So clearly, computable numbers are just a subset of programs. There are some programs that are just not of that form in the first place. They don't take integer k and output an interval. There are programs which do that, but which don't have the convergence property and are therefore not classed as computable numbers. But there are also programs which might do that, but you don't know whether or not they're going to halt. There are some programs that have that property and definitely don't halt, that you can exclude from the set. The ones that you're not sure if they halt, you just don't know if they're a computable number or not. You can tell that they're a program, but you're unsure if that program is in fact also a computable number. So clearly, computable numbers are a subset of programs. Okay. We also know that programs are a subset of natural numbers, because we can view a program in ASCII base 256. So the program clearly just is a great big natural number. Depending on how you define your language and your grammar, there will be numbers that do not correspond to programs because they're not syntactically correct. So only a subset of the integers are programs, and then only a subset of those programs are computable numbers. So this seems to suggest that there are fewer computable numbers than there are natural numbers, because every computable number is a natural number, but there are natural numbers which are not computable numbers. However, throwing words like fewer around when everything is going to infinity is problematic, because there's an unlimited number of both of these sets. The best we can do in this approach is to say that they're the same size. This is in the sense that you can pair them together. If you remember, we talked about this before. Mathematicians say two sets are the same size if for every element of one of them you can pair it up with an element in another one. So for example, the size of even numbers is the same size as the natural numbers, even though naively you think there might be twice as many naturals as evens. So coming from this side, we have a naive view that there are somehow more natural numbers than computables. When we think about it with the mathematician's definition, we can see that there should be the same. But coming from the other way, think about these numbers sitting on a number line. Here are the natural numbers and 0, depending whether you like to include 0 as a natural or not. But there are obviously many computable numbers in between each pair of natural numbers. For example, there's 1.5, there's 2.5, there's 1 3/4, there's pi, there's e, there's tau over here somewhere, and there's an unlimited number of computable numbers that can be defined in between each pair of natural. So coming at it this way, you're going to be tempted to say that there are more computable numbers than there are natural numbers, right? So this is attention, right? If you come at it from the program side, it looks like computable numbers are a subset of the naturals. If you come at it from the number line side, it looks like the naturals are a subset of the computables. And this seems paradoxical, right? Which is actually bigger, the naturals or the computables? So, to try and resolve this, let's begin by considering, can we tell whether a program P is a computable number or not? And I think we've already mentioned this. You can't, because to classify this program as a number, one of its requirements is proving that it definitely halts. And we've already seen that you can't do that. So suppose we could tell whether a program is a computable number. That would imply we can test whether it halts. But the halting problem is uncomputable. That is a contradiction. Okay? Coming out of that supposition led to a contradiction. Therefore, when we come out of the supposition, we cannot test if a program is a computable number. So keep this in your back pocket for a moment, because we're going to use it in a minute. Right, let's look at a failed attempt to try and show that there are more computable numbers than there are naturals. So this is what the mathematicians do when they claim that their real numbers are bigger than the naturals. And this is Cantor's diagonalization argument. Okay, every computable number is a program. We can write programs out in binary. Suppose for a moment we can make an ordered list of these programs. So this is one program. Okay, this is another program. This is another program. These are very short programs, but the list would go on forever. Every possible computable number program. So this whole class of Cantor arguments is based on saying, suppose you could put everything in a list. If you could put things on the list, you could then consider the diagonal and you could negate it. So we're going to come up with a new number, and the first digit is going to be 1 because it's the opposite of 0. The second digit is going to be 0 because it's the opposite of 1. Third's going to be 1 because it's the opposite of 0. Fourth is going to be 0 because it's the opposite of 1. And so on, in big quotation marks. So if we tried to follow the mathematician's argument here, we would say, we suppose we've got a list of all the computational numbers as programs. We've put them in a list and we've created a new thing from the diagonal. And this new thing was not in the original list. Therefore, we have a contradiction. Therefore, there are more computable numbers than there are natural numbers. Because anything that you can put in a list has the same size as the natural numbers. So why does this not work? What is wrong with this number that we've created here? Remember, this is supposed to be a program. All of these are binary codings for programs.
Well, you say it at the bottom, but there's no... We can choose any program we want, but there's no guarantee that that program, first of all, computes a number, and then any other requirement that we could have under what we need out of a computable number, that it holds, that it's actually going to converge, things like that.
Yeah, good. So we suppose we made an ordered list of all the computable number programs. We've created a new candidate program off the diagonal. And for Cantor's argument to work, this is supposed to be a member of the things that we wrote down in the first place. But in this case, Cantor's argument doesn't work because, this might not be a syntactically valid program. Even if it was a syntactically valid program, it might not be a computable number. It might not halt, or it might not have a convergence property. So this is a warm-up exercise. It's a naive way of trying to apply Cantor to get us in the mood. Now let's consider a second attempt, which is more serious. Okay. in this one, instead of writing the programs out in a list, we're going to write the actual numbers out in a list. So remember, we have this definition that we can write a number x as a function of d, or b in this case. Now, rather than k, we're going to use b, and that says give me b binary digits of a number. So suppose now that we've got every possible computable number and we've written them all out in a big list. Suppose that that was possible. And then we're going to do the Cantor trick on it again. We're then going to say, go off and pick everything on the diagonal and invert it. And therefore, you've found a new number that was not in the original list. Okay? So this is very like what the mathematicians do. And this one seems pretty good, right? So look, that's the supposition. Suppose that we can write an ordered list of all the computable numbers. That's the thing we're going to try and blow up. We're going to derive a contradiction. So suppose we could make a list, write them down, do diagonalization on it. We have now created a number that was not on the list. Contradiction, therefore the supposition was wrong. So if this worked, it would imply that the computable numbers were in fact bigger than the natural numbers. So any idea what is wrong with this one? Preferably without looking at the bottom of the slide. Or even with looking at the bottom of the slide, if you like.
Well, the way that I understand it is essentially you can't really begin doing the diagonalization argument because there's the implicit assumption that we can. This is one of those interesting things that you find often in philosophy or in a lot of sciences, is the implicit assumption that you can, in the first place, enumerate over a certain set. Mm-hmm. So we can actually, because we can't say how, no, we can say how each of these numbers might have been generated, but in the general case, we can't actually say whether or not this was actually, what would you say, from a computable number in the first place.
Yeah. So look, this argument is correct, right? We made a supposition. Suppose we can write these things in a list. We've got a contradiction, and the argument says, therefore, the supposition was wrong. Okay, so the argument in itself is correct. This supposition must have been wrong. Now, when the mathematicians do it, they say the only thing that could have gone wrong in the supposition was the fact that we missed out our new diagonal number. But when we look at this from the computable numbers perspective, there are other ways that the supposition can fail. So the missing out that number isn't the only cause of contradiction. So what we have here is that we couldn't have made that list in the first place because we don't know which programs halt and are therefore computable numbers. So if there might not be very many computable numbers, there might only be 10. A small finite set, but if we have no way of actually telling which ones they are, then we couldn't have made this list in the first place. So this is the big difference between what we do and what the mathematicians do. We have to construct everything. We have to have an algorithm, a program, procedure for making an instance of anything that we talk about. Whereas mathematicians are more happy to imagine senses of the world without supplying their referent. The mathematicians will say, well, there is a set of numbers that are computable. They'll say, you don't actually know which ones they are, but God does. And if God had that list, they could write them down in this order and do the proof. So therefore, our theorem is correct. So we are not happy to do that. We are only happy to accept the existence of things that can be constructed algorithmically. And at least in principle, you have to be able to write a computer program that actually gives you the thing you're talking about. So if you want to claim that a list like this exists, you've got to supply an algorithm to make the list. And the mathematicians can't do that. They just say, in theory, it could exist, or God could know what it is, even though we can't. And that's the big difference between computation and mathematics.
I feel like if you have to invoke God in order to prove that your theory exists, you're grasping at straws.
Yeah, that's probably quite a good heuristic. Yeah. So this gets pure mathematicians into all kinds of trouble. What you find in the computable number system is it's much simpler than the mathematicians' numbers. There are fewer of our numbers than their numbers, and because there are fewer, we kick out all the ones that cause problems. So many mathematicians make very successful careers out of making all this paradoxical stuff come into existence and then trying to clean it all up, whereas we just don't bring it into existence in the first place. So this is how we resolve the paradox, okay? According to the mathematician's definition of set size for infinite sets, they are both the same size. There's the same number of computable numbers as there are natural numbers. And the Cantor argument doesn't work because we have this extra restriction of construction that the pure mathematicians don't. Right, that's how you defend yourself in a fight with a mathematician. So this is a summary of what they do to make their R. So R is a much bigger set. It's a much bigger set in the sense that if you were to pick a random element from it, you would always get one that isn't in the computable number subset. So for mathematicians, pretty much every number is an uncomputable number. It's a number that doesn't have a program to generate it. Matthew?
Is it really not a superset of the natural numbers?
So R is a superset of the computable numbers.
Yeah.
Yeah. Yeah, so they will end up with all of our numbers, but many, many more. And those extra numbers are called uncomputable reals. Yeah, and there's so many of them. If you were in their model of space, imagine my meter stick with Scratch the Cat again. In the mathematician's view of the world, if you were to pick a random point on that ruler, it would not be a computable number. You'd have landed on one of these other points. And there wouldn't be any program that could ever be written that could describe exactly where that point was in space. So again, you can conceptualize this. You can, by definition, you can't give an example of an uncomputable number because the computable numbers are defined as the ones that you can give a definition, an algorithm, for getting Scratch the Cat to go there. But there are apparently all these other places on the ruler, according to the mathematicians, where Scratch the Cat could be, but you can never write a program to send him there. So for example, suppose at every step in the algorithm we halve the distance d. Okay, so initially we're going to move by 1 meter, then half a meter, then 25 centimeters. Okay, imagine you just toss the coin at every step of that process. So you have a number that is completely random. Where does that sequence end up? It's going to end up somewhere, but you have no way of knowing where it is, and you can never write a program to go there because there's an infinite amount of information in all those coin tosses, and your program only has a finite length and a finite amount of information. So you can conceive that these points might be there in someone's psychological model of space. The mathematicians like to work in that space because there are interesting theorems they can go and prove about it. But for us, we can never know an uncomputable number. By definition, if you can know the number, if you can define it, then it is computable. So they are completely useless. There's nothing we can do with them. We can never point at them. We can never name them. But there's massively more of them for mathematicians than there are power numbers. So look, in philosophy, there is a standard argument called Occam's razor, right? If you have two theories that give you the same predicted power, you should bin the one with unnecessary extra stuff. And that is what we have here. The Turing theory of computable numbers gives you the power to talk about everything which you can ever talk about and to do engineering work using those numbers. And it bins all this extra irrelevant clutter that has been introduced in the mathematicians' much larger set, unnecessarily larger set of mathematicians' real number. If anyone's looked at Keighton's book, he has a popular science book called Meta Math. Keighton is famous for defining the most messed up number in the universe, which he calls omega. And it's deliberately designed to be the most messed up number in the universe. So this is another example of an uncomputable real number. Okay, the first example was flipping a coin at every step. So omega is this crazy construction. This is an uncomputable number, so we can't actually, in fact, it's not even a construction, right? It's a conceptualization because we cannot actually construct it. It is conceptualized as follows. Okay, we define it as a sequence of binary digits after a decimal point. And to compute the Beef binary digit, you do this. Okay, you consider the Beef program in your favorite programming language, and you say, does that program halt or not? Or if it's a syntactically correct program and it halts, you get a 1. And if it is either not syntactically correct or it doesn't halt, you get a 0. Okay, so just take a moment to think about this. Like pi and e and all those numbers, this goes on forever. And every digit in that binary expansion tells you whether a program halts or not. And so this number, if you were God, and yeah, there's your heuristic. If you were God and you knew this number, it would tell you everything about the whole of computer science and possibly, therefore, all possible knowledge. It tells you whether every conceivable Turing machine in the world will halt or not. So it contains the answer to every problem, the result of every algorithm running on every problem. Again, this number contains an infinite amount of information, like containing an infinite amount of coin tosser. So, like all uncomputable numbers, there's an infinite amount of information, and that's why no finite length of program is capable of describing it. I think he's actually computed the first few digits of it, right? If you take these little tiny Turing machines with just 2 and 3 states, you can actually work out which ones halt and which ones don't. So the first few digits of it may be known for some representation. But conceptually, you have the most messed up number in the world, omega. Matthew.
I really like this book. The way that it makes me think about. I'm actually not sure if this is correct, Arthur, what you said earlier about, because he gives that argument about randomness and how that actually affects things. But the way that I thought about computable versus real versus things like omega is something like, he gives this really nice argument about space complexity, which is something along the lines of, we can say that for a computable number, because there's a representation, because there's a program, we say that there's something on the order of log n that represents this thing, versus having a real number where the upper bound, well, there isn't one. It's completely unbounded in how much spatial complexity it has. But that's not necessarily the case that any given uncomputable number necessarily has an infinite amount of complexity. It's just that the upper bound is unbounded, versus something like omega, which is just completely absurd, and we should not think about unless we want to be crazy like Chaitin.
Yeah. So a number like pi is actually a very uncomplex beast, and you can show how simple it is by the length of the program, or rather the length of the shortest possible program that exists that can describe pi. There's a good question. Can you ever know that you found the shortest program for computing pi, or could there always be a shorter one? That's a good one to think about. Beyond?
Hello. So does that mean that Deep Thought in Hitchhiker's Guide could have just given a really short rounding of omega?
What 42 is the integer truncation of omega?
Yeah. Because that tracks, right?
Yeah. If you ever want to write a fan fiction sequel,
if 42 does not turn out to be the answer to this, I am going to be like
Very
phenomenally
disappointed.
and fundamentally disappointed in the universe.
Yeah.
Good.
By the way,
so yeah,
Chaitin spelled iron. I don't know. I have the book on the shelf in front of me, and he spells it IN, but it might be EN.
I think he's actually Argentinian or Russian or something. It may be one of those names that has to be written in a different alphabet. Yeah, okay. It's not normally spelled with an I and pronounced chitin usually, rather than chai. Good. I have to fix that for you as well.
I think he's Greek, isn't he?
He's an Argentinian American mathematician, computer scientist. There's his name from the.
He's a crazy person. That's about the limit of it. It's such a fun book to read because he just he's one of these crazy people. You think, wow, that's absolutely magnificent. He's like Feynman or these great physics lecturers who absolutely there's just so much in the thing. You can tell, like, wow, it's just magnificent, wonderful.
Yeah, lots of fun to read. So that's Metamath is what it's called, the quest for omega. Okay, good. Okay, so these are some of the cracks beginning to show when we consider what's computable and what is uncomputable. Now let's take a look at the limitations within the computable number theory. So we're going to throw out all these extra numbers that the mathematicians put there that had horrible uncomputable properties, but there's still going to be uncomputable problems within the Turing system of computable numbers. So most fundamentally, it is an uncomputable problem to test whether a number is zero or not. For integers and rationals, this is very easy to do. Yeah. For an int, you just say, is it zero, and you're done. For a rational, you just say, is the top number zero? Yeah. If you're given A over B. And our assembly languages are fairly dependent on testing whether integers are zero or not. But for computable numbers, we are now dealing with programs. You're given one of those Python functions or lambda calculus functions, taking integer k and chucking out an interval approximation. And to test if a number is zero, you now have to prove whether every single digit of that approximation comes out as zero. Yeah, in the decimal sense, if you're calling the function for the dth decimal digit, you have to prove that it's going to be 0 every time. In the k definition, you have to prove that every interval coming out of the function always contains 0. The interval never goes outside of that. So whenever you come across these kinds of problems, there's a feeling you get for problems that are computable and not, and this should feel like one that is going to be trouble, because you're talking about a program that can be called in an infinite number of ways. So you could pick any value of k, and you're trying to prove this theorem saying that for every possible value of k that could ever exist, it's always going to behave in a certain way. So the way we actually prove this is going to be similar to how we do other uncomputability proofs. We're going to suppose that such a program exists. So P star is going to be our 0 testing program, okay? P star is going to take a Turing computable number as an input. So remember, T is a program. Yeah, it's an ASCII string or an int, depending on how you look at it, with the properties of a computable number program. It's going to take that program and supposedly, literally supposedly, according to the big suppose bracket, supposedly it is going to map that to a Boolean. And it's going to say, does T actually equal 0, according to the computable numbers definition of equality. So we're going to suppose this thing exists, and then we're going to cook something up to break it, and we're going to derive a contradiction, and therefore we're going to conclude that it does not exist. Right? Just like we do with all these things. You know, it's creating a record to break the record player with its resonant frequencies. The full version of this is in the abirth chapters I've given you. This could be very examinable, by the way. Well worth studying this in abirth. Okay, so before we make the supposition, we're allowed to define any functions we like. Let's define a little helper function. So this is a program called PS. This is going to take two programs, P1 and P2, and an integer, sorry, a natural number K. K is always the steps we run for. So we take two programs as input and a natural K, and PS is going to return a triple consisting of a Boolean called H and a natural called N and a rational called R. And this program is going to be a kind of virtual machine. It's going to take these two programs as input, and it's going to execute program 1 on program 2 as its input, and it's going to execute it just for k steps. Okay, so imagine it's like a debugger, and you're going to run the debugger for k steps, and then you're going to stop. And if program 1 halts within that time, which we'll see if it does, if it halts, we're going to return h equals 1, right? That's h is for halt. H equals 1 means we saw the thing halted. And if it does that, we'll also report how many steps it took to halt, and we'll also return the result. So basically, that means we chose a large enough k for the program to do its thing, and we're going to return the result and some information about what happened. If we didn't call it with a large enough k, then we're going to return h equals 0. We're going to say it hasn't finished yet, and we'll just bung 0 in the other two outputs so that there's something there. Okay, so this is a well-defined little function. Right? So a little debugger virtual machine emulator kind of function. Okay, so now we've made this supposition, we're going to assume that our magical 0 testing program exists called P star. Okay, and now we're going to do our usual thing. We're going to cook up a record to put in the record player in order to break the thing. And we're going to call this Z in this case. And Z is a computable number program. It's taking D as an input because it's going to do it in decimal place digits. Okay. z of b. Right, what are we going to do in this function then? We're going to go out and call our virtual machine, our PS, right? We're going to say go and spend some time running the is0 function, and as usual we're going to run it on ourselves. We're going to pass it our own code, the code for this function z. We're going to pass it a copy of our own code as an argument. You need to do some quining, like we saw with the lambda calculus example, to actually get the program's own code to go in there. Right, so we're going to take our magic zero function, we're going to give it ourselves as an argument. So this function is now going to analyze us and say whether or not we output a zero. Yeah, and by now you should be able to see where this is going to go. Yeah. We're going to run it for, in this case, d steps using our virtual machine thing, and then we're just going to contradict whatever comes back, right? If the zero function says that I do output a zero, then I'm going to deliberately output something that isn't zero. If it says if it halts and the result is zero. If it halts and it says I don't output a zero, then I'm going to deliberately output a zero. Okay. And if it doesn't halt, I'm still going to output a zero. So there's a little bit of extra trickery. Remember, we can't just output a pure zero because we're always dealing with these intervals. So if you work through this in our birth, you'll see exactly why you need to output zero to this level of precision at each step. And in this case, there are three possibilities. The thing can output a zero, and if it does that, then we output a one. If it outputs a one, then we'll output a zero. But as well as that, it might not halt. If the zero testing function doesn't halt, then it just doesn't work, because we initially supposed that it works, and that includes halting. So if you put together all three of these cases, you still end up with a contradiction, and therefore the zero testing function does not exist. Okay? It's the same basic plan that we've seen in all of these. You suppose the thing exists, you cook up a destroyer for it, and the destroyer has this property of using itself as an argument, and then it's going to contradict itself. So it's just another programmatic version of all lecturers are liars, right? So we cannot test if a number is zero in general. In a lot of cases you can. Don't be too upset by this. If you just have the number 3, you can perfectly prove that 3 is not zero. But in the general case, if I give you an arbitrary program, some of those are going to be impossible for you to test. So, following on from this, you can't test if a number is zero. What does that mean, right? Zero testing is incomputable. So now let's make another supposition. What would happen if we had an algorithm for testing if two numbers are equal? Yeah, two computable Turing numbers, T1 equals T2. Right. If we make that supposition, we could then make this alteration to the equation. We can subtract T2 from both sides. And so testing for equality is equivalent to testing whether this number is zero. And that contradicts what we just saw, that you cannot have a test for zeroness. So therefore, testing the equality of two numbers becomes uncomputable. Okay, so now you can keep going. How about testing if one number is bigger than another number? So logically, testing T1 is smaller than T2 is equivalent to saying it is not the case that, have I got this the right way around? It's not the case that T1 is smaller than T2, and it's not the case that T1 is greater than T2. No, that's not equivalent. This is just something we're going to consider, all right? So let's suppose we can make these comparisons, yeah? under that supposition, we're allowed to just invent this expression and we're going to consider it. Okay, so if we have a test for doing that, we can create this new thing that says it's not the case that 1's less than 2, and it's also not the case that 1 is bigger than 2. Okay, and that is equivalent to an equality test. That's the way this one works. Right, so if you could test for less than, you could always create an equality test, and we've just shown that equality is uncomputable. So therefore, this thing doesn't exist either. We're going to knock down this supposition. Okay, and just to complete the set, the other operation is less than or equal to. This is equivalent to testing the other side. This is just logically equivalent to T2 is greater than T1, and we just showed that that was uncomputable, and therefore this is uncomputable. So beginning with zero testing being uncomputable, we've shown that all of these comparison operators become uncomputable. Okay, so another consequence of this is a limitation it puts on function definitions. Okay, let's consider what does a function of a computable number look like. So we've seen operators already, addition, subtraction. This is actually a simpler case. This is just functions of a single variable mapping from computable numbers to computable numbers. So any function of computable numbers is going to have this form, right? It's going to be something which takes a program, it takes the computable number as an input, and it takes k as an input, and it's going to return the kth value of f of p, where f is the function you're trying to represent. For example, you can define a doubling function, right? This just takes the computable number as input and it doubles it. So, done this one in lambda notation, right? This is going to be a function which takes a program and an integer. And remember, all these things have to return pairs. They've always got to return x and e because they're returning an interval. So we're going to return a pair, and it's going to double the main number. Like it calls p to approximation k, doubles it, and then it computes the error. It takes the second term, which is e, out of that and doubles that. So this is using the lambda notations that we built up. Remember, we defined pairs and how to pick the first element and the second element, because we're always returning these pairs of x and e together. Sometimes it can be tricky to keep choosing these e's correctly. I chose doubling because it's especially easy to figure out what the e needs to be. Remember, you've always got to choose your e to show that that convergence property exists. So sometimes you have to think a bit harder about how to do it. But look, there's a limitation on what can be done with this type of function. So it will turn out that functions have to be continuous. If you set up your mathematics based on Turing computable numbers, all functions are continuous. So in particular, you cannot have a function like this. Okay, this is a function called threshold, which is 0 if x is less than 0, and it's 1 if x is greater than 0. Well, be careful what you do on the 0 point. In this case, it's defined as less than or equal to 0. So you can't create this as a computable function anymore because you can't compute whether x is actually 0 or less than 0. Okay, there'll be programs which give you a number that is very close to 0, and you don't know whether they're 0 or not. They could be outputting 0.00000000000, and then you run out of k, and you have no idea if they're going to continue outputting noughts or if they're going to output something else to become non-zero. So you can't construct this function in the computable number system. Now, what you can do is make functions that are as close to it as you like. So here we've got some sigmoid functions like you find in neural network theory, and you can start with a sigmoid function like that, and then you can tighten it, and you can make it go closer and closer to looking like that threshold function. You can tighten it up all the way like this and make it as close as you want it to be to the threshold, but you never actually get there. And this again is a good thing, because a lot of the problems that mathematicians have when they do analysis is in sorting out the mess that comes from assuming stuff like this existed in the first place. You get lots of these paradoxical results and they have to develop extra theories to handle them. But in Turing's approach, none of that existed. Everything is nice and continuous, so your calculus is going to work very nicely. You're not going to have to deal with zeros and infinities and all forms of badness when you get into differentiation and integration, for example. Turing didn't work on that stuff, by the way. That was developed by a bunch of other people, lots of Russians and Rice and Specker, the people who came after Turing and built on his work. And you can read all about that in Aberth's wonderful book. Yeah, that book's going to go through and it's going to rebuild A-level calculus out of computable numbers. Basically, you're going to define differentiation and integration all in terms of programs acting on other programs. So this is kind of worrying, right? Testing if two numbers are equal is an uncomputable problem, and all these problems that then hang off of that. Testing if a number is bigger than another number, or if a number is zero. When we go to Rice's theorem, we're now going to leave numbers behind, or numbers are just a special case of programs in general. We're going to apply some of these same arguments to programs in general. Okay, so remember, a computable number is a subset of programs. It's a program that has certain properties. And to do mathematics, those are the only programs we're interested in. To do computer science, and especially anything to do with static analysis, we are more interested in the entire class of programs, not just that little subset that the mathematicians deal with. We want to handle all of them. But again, Rice came after Turing, 1951. And Rice generalizes those ideas that came from computable arithmetic into general analysis of programs. And in English, Rice's theorem is this epoch-making statement that all non-trivial properties of programs are uncomputable, which sounds kind of bad, right? This pretty much sounds like the end of computer science as a subject that would like to make statements about properties of programs in general. So this applies to the special case of programs that are computable numbers, but also to all the other programs as well. So how are we going to do this one, right? It's the usual pattern. There's going to be some supposing, there's going to be some contradicting, and then there's going to be some thereforeing, okay, as usual. So let us suppose that some property of programs P was computable. And this could be absolutely anything. So for an example, let us consider the property of being a squaring program. So this is the property that we just saw Ching prove with his verification. Okay, we prove that program, or at least we prove that at the end of that program something is equal to something else squared, which is not quite the same thing as being a squaring program, as we saw. But let's consider the property of being a squaring program. Okay, in general, this property could be anything, but we're going to consider it being a squaring program so that we have a concrete example to think about. So I'm going to give you a program. It might be 2,000 pages long, and your task is to say algorithmically is this a squaring program or not? And we're going to show that it's not possible to test for that property. And the way we're going to do it is by reducing it to the halting problem. We're going to show that if this was possible, then you could go and solve the halting problem. So keep your property program in your back pocket for a moment. That's phi. Okay. Now consider an entirely separate program, A, and this is an arbitrary program, and it could have an arbitrary input I. Okay, this could be any program in the world, nothing to do with the property you're looking for. So we've now got two programs. We've got P, which is the thing we're testing for the property, and we've got A, which is any arbitrary program that we're going to solve the halting problem for, supposedly. Right. Now we've prepared those, let's cook up our breaking it function, as we always do. Right? We're going to make something that messes everything up that is impossible. So this is a little function of n. Remember, n is the thing that the squaring program is operating on. This is a little tiny function of n, and basically it's just a wrapper for this line here. This line is going to, depending on the property you're looking for, it's going to do some operation which actually has that property. So this is why it's nice to have the squaring example. In this case, the property we're looking for is, are you building a squaring function or not? So for that example, we're just going to square n. We're going to do the squaring function. So whatever property you were checking for, we're going to ensure that that property gets done at this point. Okay, so for example, returning n squared, if you're looking for a squaring function. So the point of this line is to guarantee that the property you're testing for is true. Okay. Now we're going to break it by putting this line before. And this line, this has nothing to do with the property we're looking for, and it has nothing to do with input n. Okay, this is running on two entirely separate things, A and I. And remember, A can be any program and I can be any input. And all we're going to do here is run an arbitrary program on an arbitrary input. Okay, that has nothing at all to do with the property that we're testing for. So we're doing two totally separate things. We go and run an arbitrary program on an arbitrary input, and then we go and cook up a state so that the property is satisfied. Okay. So what's going to happen here then is all about this AI. Okay. Now, A is an arbitrary program, I is an arbitrary input, could be anything. And we know that in general, it's not possible to tell whether A will halt given input I. Okay, so this line might halt or it might not halt. If it does halt, this program will actually execute. It will get past this line. Then it will go and cook up the property we were interested in, such as making a squared program, and return it. If this thing doesn't halt, then the whole function doesn't halt because it gets stuck on this line. Okay. So here's our killer function. Yeah, we're assuming that we have this property checker, and this could be for any property of program P, such as squaring, but it could be absolutely anything at all. If that checker existed, we could solve the halting problem because we could call this function. If A of I halts, then the result of the whole thing will be true because it deliberately then creates a state where the property halts. If the thing doesn't halt, then the property checker that you claim to have invented would have to be able to detect that. You would have to tell that AI doesn't halt in order to know that this line was never going to be executed. So we can therefore reduce the general question of asking for any property of any program to a version of the halting problem. So detecting whether any property of a program holds is an uncomputable problem. So all the uncomputable problems we've seen in arithmetic, like checking if a program is equal to 0, is a special case of this. It's a property of a program that it gives a computable number equivalent to 0. Checking that a program is less than another number is another property. But Rice's theorem takes that way beyond Turing's computable numbers and into pure computer science now, because it's any property of any program. So, here are some properties of programs that we would really like to be able to test for, and Rice's theorem shows that we can't. So, does a program fulfill a set of void-or assertions? Yeah, that is a property of the program, and it's something we can apply Rice's theorem to show that it's an uncomputable problem. In the general case, you can do it in some cases, as you're doing in your assessments, but you can't do it for every program and every property. Testing if it computes the same thing as another program, yeah, which is one definition of two programs being equal. So you can't prove if two programs do the same thing, because that would be a property of at least one of them. If you can't prove that two programs do the same thing, you therefore can't prove that program X does the same thing as program B and is also shorter or faster. And if you can't do that, then you can't find the shortest program or the fastest program that is equivalent. Okay? So this means it's an uncomputable program to write a perfect optimizing compiler, because you cannot take a program as input and find an equivalent program that makes it go faster or as fast as possible. Finding the optimal compression algorithm. It's a property of a program whether or not it is an optimal compression algorithm for a particular type of data, and you can't prove that that property holds by Rice's theorem. Now, all these things you'd like to have in your static analysis tools. Is this code dead? Is it a property of a program that some lines will never be executed? You can't test for that property because you'd violate Rice's theorem. You'd like to say, do any inputs make my program crash? That's a property of the program. Does a program have a property that this piece of memory will not be accessed again? Can my garbage collector actually run now? Or is there a chance someone's going to come back and look at the area of memory? All of these things are properties of programs, and they're all going to fall foul of Rice's theorem in the general case. Which seems like bad news for your career in static analysis, right? If anyone was hoping to join the Microsoft Visual Studio team and implement coding assistants that test for these things.
Isn't this brilliant news? That means that we're never out of the job. This is fantastic.
Almost like I planted someone there. Right. Yeah. Okay. Absolutely. On the flip side, that's the downside of uncomputability, right? The flip side of uncomputability is called full employment. You can take each of those statements and convert it into a full employment theorem for people who do that thing. So yeah, these results only apply to the general case. Okay, they're not saying that you can't do that stuff for some programs, or even for very large and useful classes of programs. But they're saying that you will never find one algorithm that does it for every program. So it's saying you can go off and come up with new algorithms all the time, which can solve those problems for more and more special cases, for larger and larger classes of programs, but there will always be work for you to do, because no single algorithm can solve it. You can always go and find a better one that works a little bit better. This is a similar story to what you find in NP hardness. NP hardness is often taught in a very old-fashioned, non-probabilistic way that I don't like. The traveling salesman problem is NP hard, therefore don't try and solve traveling salesman problem. Whereas what actually happens, and I've worked on actual traveling salesman problems, as in routing vehicles around motorway network. For most practical cases, you can find good algorithms for those problems. The fact that a problem is NP hard only means that there exists at least one input that takes you that long to solve. It doesn't say anything about all the other 99.999% of cases, which might have a perfectly good heuristic that works most of the time. So, as with NP hardness, we're only talking about what you would conceive of as a small number of cases. The notion of small is difficult because there's an infinite number of everything. But it's small in the sense that if you were to pick a random program, you're probably going to get one that you actually can do this stuff rather than one that is problematic. But no one's ever going to come up with the one algorithm, so there is always going to be jobs at Microsoft Research developing a slightly better version of Visual Studio with a slightly better set of tools. Just like the stuff you saw the VCC team doing. They're constantly adding new heuristics to that Floyd-Hoare analyzer to make it work in more and more cases. So, in practice, it is very often possible to tell if a number is greater than another, right? 3 is greater than 1, then that's an easy problem. Uncomputability only applies to the general case. It just means if you claim to have found a function that compares any numbers, I can always go and cook up a problem that is too hard for it and break it. So yeah, often you can tell if a number is greater than another. Often you can tell if a theorem is true. You can often find a proof of something by applying some creativity in obvious quotation marks. Often you can prove that two programs compute the same thing. Floyd-Hoare logic with some creativity is again a way of doing that. It's a property of the program that it computes the same thing as something else. And therefore that one program is an optimized version of another one for certain cases. So not only is this possible, but you can often prove that there are these inexhaustible supplies. Okay, so it's a trendy thing now to stop talking about uncomputability and undecidability, which are negative words, especially for funding agencies. Why do I want to give you £10 million of taxpayers' money to show that it's not possible to do a whole lot of things? Right, if we talk about inexhaustibility, this is the positive flip side. It means that there is always good work that can be done. There are always good places for your career in static analysis to go. You may find those careers quite frustrating because you're never going to find the perfect algorithm. You're going to end up, like most of computer science and AI, going to conferences where there's 100 people all proposing slight variations of heuristics for solving a problem in a couple more slightly larger cases. You might feel that it's not making progress. It is solving the problem for larger sets of cases, but it's never going to really give you the theory of the problem because it's uncomputable. And that's what the world is like in many of these research communities. Compiler writers, mathematicians, automated mathematician, theorem provers, AI, all of their conferences have that kind of feeling to them. Lots of heuristics, no general solutions, because they're uncomputable.
I believe you're disconnected, Charles. Hmm.
Right, go on then, Matthew, take over.
Yeah, oh well. That was good. Man. Gone. He's fed up with us.
Rip.
It was too uncomputable. Just couldn't deal with it.
Yeah. I wonder how it does apply in networking situations. I bet networking engineers never cared about whether it was possible to send something from one end of a network to the other. It's,
Only the first time. Other than that, it doesn't matter. Anything else doesn't matter.
yeah. As long as we hit like the 99%.
My
Hello?
computer just crashed. This is
It
Debian.
crashed.
Yeah, how
Crashed.
did we do? What a moment to crash. Debian doesn't crash. It just did.
Debian does crash if you run massive JavaScript applications in your browser.
I think it's trying to tell me something. Anyway.
Operating systems. Incomputable.
Some examples of uncomputability spilling out into really practical cases, right? There's a whole class of equations, or Diophantine equations, which show up in many problems in operations research. You know, you're scheduling trucks and taxis, and there's an integer number of everything. What on earth has happened to my equation? That's not plus 2, is it? That's Diophantine equations are polynomials in integers. That's still not right, is it? What's the Pythagorean theorem? 25 equals 3 squared plus... yeah, 3 squared plus 4 squared plus 5.
Correct.
Yeah. So that equation has an integer solution. You can find the integers 3, 4, and 5 and solve that equation. Fermat's last theorem is another case of that, which was very hard to solve. But you can show formally that this whole class of Diophantine equations, i.e. polynomials with integers, is generally uncomputable to solve. And you know, these are equations that come up in trying to schedule your fleet of discrete taxis and so on in operations research. Type inference for second order logics has been proved to be uncomputable. Okay, so second order logic, we talked about first order logic. Second order logic is where you're allowed to do this. You're allowed to quantify over functions as well as variables. Okay, this is saying for all functions of x and y, some property holds of the function. So we would like to have programming languages that can talk about functions like that, but if you do that, the type system becomes uncomputable. So you're not going to be able to do all the clever stuff we've seen in automated type systems theory. It shows up in robotics when you get to, has anyone come across POMDPs? Okay, POMDP is a planning algorithm, partially observable Markov decision processes. Life is a POMDP. It's the general task of deciding what actions to take when you don't know what's going to happen or what information you're going to get as a result of those actions. Things show up a lot in games. Conway's Game of Life. Can you determine if a given pattern is ever going to form from a starting point? No, uncomputable. Determine if a player has a winning strategy in Magic the Gathering has been similarly shown to be uncomputable.
Technically, actually, I think that might not be true. Magic the Gathering has been proved to be Turing complete, but only in a very, 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 well, like you said, it's the 99.9%, but within like regular rules, you have limits like you can only have you can only have up to 3 of a card, and that kind of shuts down computability in MTG.
All right, go and dig out the details of it. Yeah. But yeah, more worryingly, these give you an indication that game theory in general is going to have these problems. So the game theory is the theory of multiple agents interacting with one another. So you have to predict what the other player is going to do, but they're predicting what you're doing at the same time. So this is going to show up in quantitative finance, where you're trying to figure out where the market is going to go when everyone's watching each other. It's going to come up in the work we do on self-driving vehicles at the moment. We apply game theory to studying how pedestrians interact with oncoming cars, and specifically who's going to get out of the way when to avoid a collision. What you have there is this problem that you're trying to guess what the driver does, but the driver's trying to guess what you're doing. And so part of your job is now to predict your own behavior. You're trying to predict the driver's prediction of your own future behavior. And as we've seen, when you have functions that try and predict their own future behavior, that's when you start getting into trouble with these things. So, we're currently interested in this idea, is crossing the road an uncomputable problem? Yeah, deciding when to step in front of a vehicle may actually turn out to fit into this class, which is going to give the Law Commission a great time deciding who to blame for an accident if you can prove there was no computable solution to who was supposed to step out into the road. Matthew?
I think, even more generally than that, constraint optimization and constraint satisfaction problems seem very in the region of uncomputability.
Mm-hmm.
So if we're talking about game theory more generally, if we're trying to optimize for a given region or a given set, then that seems already very non-computable.
Yeah. So it's a problem with the way we teach you guys. Most courses you take will be, here is a bunch of algorithms that solve a bunch of problems, but we can only teach you the algorithms that exist. And it's now appearing that there are many more problems in the world that don't have algorithms to solve them. And they're all the things that you've never noticed because you've been only fed with problems that do have algorithms that you can be taught about. So this is uncomputability everywhere. We started with Turing's numbers. We built arithmetic out of those numbers, talked about the size of those numbers, how they compare to what the mathematicians do with their numbers, and how ours are better. And then we started looking at limitations of that number system. There's not as many as there are with the mathematicians' real numbers. We cut out a lot of those problems, but there are still problems that are uncomputable. And then we generalize them away from programs that are numbers to programs in general with Rice's theorem. Rice's theorem says all non-trivial properties of programs are uncomputable. And we've seen examples of that here in the real world. This stuff is very examinable. Okay. So I think we'll stop in a moment. If you guys would like to continue the discussion amongst yourselves, maybe on another day now. A very good topic to discuss would be, why is it impossible to know if two numbers are equal? All right, and how much of a problem is this in the real world? Okay, that would be a very good thing for everyone to discuss over the next week. Any other questions?